Welcome back to the channel, guys. Hope you are doing extremely well, and this is lecture number 16 of the linked list series. Hope you are liking the series and you are following it too. Now, the problem for today is intersection of two sorted linked lists. Intersection of two sorted linked lists. What does it say? It will provide you with the head 1 of linked list 1 and head 2 of linked list 2. Now you have to give me a linked list. You have to give me a linked list which only comprise of the nodes which are common to both, such that you can see that 2 is occurring here also and here also. 4 is occurring here also and here also. 6 is occurring here as well as here. So my linked list answer will look something like 2 connected to 4 connected to 6. Right? This will be my answer. Now your aim is to take these two as input and give me this output, right? Give me this output. How will you proceed? How will you proceed? So as usual, we will be discussing our brute force approach first. So the brute force approach says that traverse either linked list, traverse either one linked list, either linked list, either linked list. Let's say you are traversing head 1, right? You are using traversal for head 1. Now what will you do? You are initially here at temp. Now your approach should say that I will traverse the whole linked list 2, 4, 6, 8. I will traverse the whole linked list. If I find a value that is equals to this value, that means this node actually exists here also and here also. So I will say traverse either linked list for each node, traverse other linked list, other linked list. If you are able to find a node such that one's data, that is traversal, that is temp1 data, equals to 2's data, that means the node is present in both the linked list, right? Add it to your answer. Add it to your answer. So what I'm saying is, the algorithm says that you have 1, 2, 3, 4, 5 right here. Oh, sorry, what was the linked list? It was 1, 2, 3, 4, 6. It was 1, 2, 3, 4, 6. And another one was 2, 4, 6, 8, right? Now what will I do? I will keep a temp1 here, I will then traverse, but before, because I want the answer linked list, what will I do? I will create dummy node. So -1 is my dummy node and A. See, when do I use this dummy? When I have to turn a linked list as an answer, a modified linked list as an answer, then I will always use dummy. Okay. So when do I use dummy? I use dummy when I want the linked list as an answer, right? I want a linked list as an answer. I want a linked list as answer, and that is when I will be using dummy. So my temp1 is here, right? My temp1, for my temp1 I will traverse this linked list, that is temp2. Is it equals to 2? No. Now I can optimize it. How? If I know that these two lists are sorted, right? So what can I do? I will say that if if T2 data is greater than T1 data, you can break. Why? Because if you are not able to find a value up till this node, then it is not possible to find a value in this node, because these values are actually going to be greater, but you needed a value which is equals to T1, which is actually smaller than this node as well, right? So I will break it up here only, right? My first condition is if data equals to right? If both data are equal. If that is not the case, and if data is greater, I can simply break. But if the case arises that if they are equal, then I will be adding the node. So I can see 1 is not present, so I will move my T1 here. Now for 2, I will see that T2 is actually pointing to 2. So this is a node. So I will break, and I am able to see that I have to add this node into my linked list. So I will actually create a new node such that this, right? Because making the connection and breaking the connection here would be somewhat difficult. So I am making a new node here only. A, and moving forward, T1 comes here. Again, check it out. T2 comes here. No. T2 comes here. 4, actually greater than 3. Not found a value. That means 3 is also not a part of the intersection linked list. T1 comes here. Again, T2 is here. T2 is here. T2 comes here, and I will be able to see that 4 equals to 4. So add it to your answer linked list. 4 is here. T1 is here. T1 is at the point of 6. So T2 again comes here. then here, and then here, and I'm able to see that 6 is a part of my answer now, right? And then T1 becomes null, and that means the intersection linked list is 2, 4, 6. It is easy to delete just this node, and my head will be here, right? Okay. But what is the time complexity now? So you are able to see, suppose this is length n1 and this is length n2, right? This is length n2. So now you are actually traversing this. So O of n1 is for it, right? O of n1 is here. But for each node, you are actually traversing the whole linked list. So O of n2 also. So it is actually becoming O of n1 into n2, somewhat closer to a square time complexity, not an optimized solution. Square time complexity. And also you were able to see that we are actually creating new nodes. So it is actually using some extra space, right? Now, what can I do to get my answer fastly? Fastly, that is, I have to reduce the time complexity, and I also want to decrease the time space complexity, right? See, this approach can be used for unsorted linked list also. For unsorted linked list, how? If I just remove this pointer, this is actually working for unsorted linked list, right? So it is not very much optimized for the sorted linked list part. I just want a solution that is actually very much optimized for a sorted linked list, right? For a sorted linked list. That should be my key here. See, whenever the question provides you with a sorted something, then it means that you have to think some way, right? Now, the given linked list to me is 1, 2, 3, 4, 6, and the another one is 2, 4, 6, 8, right? Right now my temp1 is here, my temp2 is here, and I have already created my dummy node -1, right? This is my dummy here, and I will make a pointer a, that is for adding a nodes, stand here. Now my approach says that there can be three conditions for current temp1 and temp2. What are the three conditions? T1's data equals to T2 data. This can be the first condition. Second condition is T1's data is greater than T2 data. And the third condition is T1 data is less than T2 data. These are the only three conditions that can occur. First condition is this, second is this, and third is this, right? If this is the case, the first one is the case, then it is pretty evident that they are present, this node is present in the link intersection linked list, right? Okay. Now, but for the given case, it's 1 less than 2. T1's data is actually less than T2 data. This is the third point actually happening in the first case. 1 is actually less than 2. So now my approach says, because the linked list is sorted, I want to find an intersection. See, T2 cannot move backwards. T2 cannot move backwards. If T2 is present here, and T1 is present here, T1's data is less than 1. T1 data is 1, T2 data is 2. So if I want to find an intersection, I will have to traverse one side, right? Either T1 can move here, or either T2 can move here, right? Now, because data of T1 is less, T1 will now try to find the data of T2. T1 will now try to find the data of T2. Please understand carefully, because the value in T1 is actually less, then T1 will try to find T2. Now, if you can see that, why will T1 try? Because it knows that it is not possible to go backwards, first point. And second point, I have already come from back only. And there was no intersection with T2. So, I will be moving forward. If T1 comes here, and I am able to see now that T1's data is equals to T2. So, what is happening in T1's data less than T2 data? It is for sure that T1 and T2 does not have an intersection. It is for sure that this node does not have an intersection in this linked list. Why? Because if it had been having a intersection, then that node would have occurred before current T2, right? So I will be deleting the node of T1. So first delete T1. The standard procedure, first keep a pointer x there, and T1 will move to next, and then you will delete it. So delete x, I am mentioning delete x, and T1 is actually now here. Now the case arises, T1 data is actually equals to T2 data. The case arises is this case, equals to. So what you will do? Now whenever they are equals to intersection, right? So what you will do? A is next equals to T1, A becomes A next, T1 equals to T1 next, and A is next equals to null. This is your point. You have actually deleted this node, so I am just rubbing it out right now. So what happens is, you have actually joined this A with T2. You have actually joined this A with T1. Now, because this linked list has this node has been covered up, I can also delete this node as well. Because I have used this node, intersection is formed, I will also delete this node. So I will be deleting this node as well, and I will be moving T2 here. So whenever there is a data, connect A with T1. You can also use T2 here instead of T1. It is your choice. Then connect A with T1, move T1 and then delete T2. Delete T2 means actually why we have to remove the T2 by keeping in pointer X there, right? Again, 3 and 4. Is 3 greater than 4? No, 3 is actually less than 4. So you are able to find 4 only on the right. So T1 will move here, delete this node, right? 4 equals to 4. Again, this will form. A will come here, T1 will come here and break the connection. So T1 is not actually here, now it is here. Moving on, 6 greater than 4. The case arises that T1 is actually greater than 4. So as T1 moved, now T2 will move, right? You have actually deleted this node also before also, okay? So 6 actually equals to 6, sorry, 6 actually equals to 6, so you will connect it, right? You will connect it, and now your A1 is here, T1 is here. As soon as your T1 becomes null, it is no longer possible to find an intersection. So you will say my linked list is -1 2 4 6, and you will after that delete your -1 because it is a dummy node, and your linked list is 2 4 6. Your linked list is 2 4 6. So what have we done? We have actually used this pseudocode. What have we done? T1 equals to head 1, the first linked list. T2 equals to head 2, right? After that we created a dummy node. Dummy equals to new node. Assign it any value you want, a, right? -1. A equals to dummy to add it, to traverse it. Now my linked list will move up until T1 and T2 both are not equal, to null. The first case is if T1 data equals to T2 data. In this case I am choosing T1 to add the node, so A next equals to T1, T1 equals to T1 next, A equals to A next, and A next equals to null. A next equals to null. But same time delete the X node also. So X equals to T2, T2 equals to T2 next, T2 equals to T2 next, and then delete X because that is no longer needed. Moving on. Else if T1 data is less than T2 data, T1 data is less than T2 data, then you will have to move T1 forward. But before moving T1 forward, you can actually delete this node to free the space. So X equals to T1, T1 equals to T1 next, and then you can delete your X, delete X. Moving forward, else case, the thing you did for T1, you will do the same for T2. That is X equals to T2, T2 equals to T2 next, and then delete your X, delete X, right? Else block finished, while loop finished. After while loop, just delete your dummy, that is X equals to dummy, head equals to dummy next, and you can delete your X now. So delete X and return your head, delete X, return head. That's all, matter finished. And this is the only thing you have to do for writing the whole code. So now let us move to the code. Hope you were able to understand it. So let us now move to the code. So guys, we are standing at the coding platform. This is GFG we are talking about, and now I would like to request you to please, if you have not subscribed to my channel yet, please give me a subscription. And if you are learning anything, do not forget to like. Okay. So first is node star dummy equals to new node -1. You can use either values, right? Node star A equals to dummy. At the same time, T1 equals to head 1 for traversal, and T2 equals to head 2. Right? Moving on, while T1 and T2 both are not null, what will happen? The first case is if T1 data equals to T2 data. What will happen? You will just join it. So A is next is equals to T1, A equals to A next, T1 equals to T1 next, A is next equals to null, right? And at the same time delete the T2 node because that is no longer needed. So node star X equals to T2, T2 becomes its next, and you can safely delete your X because that is no longer needed. Moving on, if the else if case arises, that is else if T1 data is less than T2 data, what will you do in this case? You will move the T1 next, and before moving you will delete the X node because that is no longer needed. Thus current T1 is not needed. That will never find an intersection. So T1 equals to T1 next, and now you can delete your X, delete X. Just in the else case, just repeat the cycle for T2. So T2 node star X equals to T2, T2 equals to t2 next, and delete your x. After the while loop ends, you have your dummy node and the answer linked list. So you will delete the dummy node. So node star head equals to dummy next. Safely delete your dummy node. So delete dummy, and now you can return your head. Return head, right? Hope it will work. Let us try to compile and run it. In the meantime, I'm requesting if you're new here, do not forget to subscribe. So it is running fine. Let us try it for submit as well. Hope it will work fine. And it is running, and it is running. It is running fine. So thank you for watching and have a nice day. We'll meet again tomorrow. Till then, please stay tuned and keep coding. Thank you. Have a nice day.